Hi everyone, I'm Lucian and I'm part of a larger team in IBM Research at Almaden, working on building the next generation of tools that enable the human-machine co-creation of explainable AI models for data. So a lot of focus in our work is on dealing with hard heterogeneous data and in curation of such data. So, needless to say, data is at the foundation of many of the systems and applications that we are building, not only at IBM, but in many places in the academia and industry. We have large amounts of non-traditional data that are produced by several sources, and this complements the more traditional type of structured databases that we had in the past and we still have. So you can also see the dichotomy between the open data that's available as public data sets or subscription data sets and enterprise data. So, however, having said that, many of the AI systems, and especially those that need to face the users, the domain experts that need to solve real-life world problems, the AI systems that support such users need good data in the form of knowledge graphs that can enable then more informed decisions, or labeled data sets and ground truth data sets that can be used for better training of AI models. So producing such good data is essential, and this is a challenge, but it can also benefit from good AI tools. And this is where we come. So our focus is on building AI tools that can assist the human experts with their data curation needs. So just to give an example out of many possible applications, so imagine that you have an expert who may be working for a regulatory agency or for investment management firm, and he or she is interested in gaining insight about the financial health of a company. In this case, we want to be able to find the counterparties and the risk associated with the various counterparties and other types of exposure. So what's needed here is highly structured and curated data that can support this type of experts. However, the data is in raw documents. It's fragmented across filings that are submitted by the various companies. The data is in PDF, HTML, in text. So we need to be able to identify the important pieces of data and then put them together in something that's of high value. So there is a gap here that must be bridged. And today, financial data providers employ thousands of people to actually manually curate such raw data and provide integrated content. So this slide is a high-level overview of the work that we are doing in this space. So our work falls under this umbrella of the AI life cycle for knowledge creation, which has multiple stages. The first one is one in which we make documents consumable by machine. And we use here various combinations of OCR techniques to process PDF documents. And also we pay a lot of attention on understanding tables, since tables often carry a lot of information that can be useful for the domain, for the specific domain. The second phase is one in which we go deeper into understanding the contents of the documents. So here we use NLP and the language analysis. One of the main area of focus here is the universal semantic understanding of language, where we want to build a representation that's actually agnostic of the actual language, which can also enable better domain adaptation. We are also working on contextualized table understanding. So as we extract and identify tables and their contents, we want to be able to relate that to the surrounding text in the documents. And this brings up, this type of linking brings us to the third stage, which is the entity resolution and entity fusion. The idea here is that as we extract data from all of this variety of documents, data sets, we want to be able to link them and put them together into something that forms a knowledge graph of entities and relationships. And we work here on two different aspects. One is entity normalization and variant generation for the various, for the string representations of the various entities as they appear in text or other data sets. And the second part is actual entity resolution, which is the ability to link sets of structured records. And in this space, we are focused, as I said earlier, on human-in-the-loop tools that address the various tasks here. And the other important factor that I should mention is explainability, which is particularly important in industrial settings. We want to build the models that are explainable, that an expert can take and further customize and tune to their particular problem. So just to make things a bit more precise, we can take a look at the anatomy of, the general anatomy of a human-in-the-loop workflow for model development. So there are actually three phases in model development, roughly. Data labeling, the actual model development, and then the deployment and feedback. So for data labeling, the important part is how do we acquire the labeled data? We can use domain experts, which will surely give higher quality for the labeled data, but we can also use crowdsourcing, and we have projects that are that use crowdsourcing to acquire labeled data for various NLP tasks. Then the humans can be involved in the actual learning of the algorithms, of the models. So typically here we would have an AI engineer that provides feedback to the learning system. And we'll see quickly an example of active learning system where the machine interacts with the user to acquire labeled data on demand. Oftentimes we also need to instill external knowledge that may be coming from taxonomies or ontologies into this, into the models that they're going to be learned. And of course there is, we need to have humans in the evaluation phase, and the fact that the model is explainable enables an engineer to actually customize the model. Oftentimes the machine learning algorithms may overfit to the data, may still need to be, the result may still need to be customized. And there is another feedback loop from the actual end users or the domain experts using the tools. So having said that, let's take a look at two examples of systems. So I'm highlighting here two. One is on text analysis use case, motivated by one of our products, Watson Discovery. So the problem here is to be able to build a model that can classify sentences in legal documents. So these sentences, so this is imagine you have a database of sentences, and we need to label them as into one of many labels, such as communication, warranty, intellectual property, and so on. So in this system, the way we approach this, we have a deep learning model that learns rules. These rules are based on linguistic predicates that apply on top of semantic parsing of natural language. And once the rules are produced, there's a customization phase. So we have a user interface where the NLP engineer can further customize these rules. And you'll see screenshots of our system in a slide. The second application that I want to highlight is the entity resolution. So imagine here that we want to match entities across two very large data sets. Let's say I want to match IBM employees and find those who frequently tweet on a specific topic, that are expert on a specific topic. So this requires matching. In this system, we use active learning to acquire the labeled data as needed and learn again a set of rules. So these rules are similar to the ones we learned in the other scenario, except the predicates are very different. So these are predicates that are specific to entity resolution. And again, this type of active learning system will work well in situations where you don't have much labeled data. And this is often the case when you go to a industry customer. They will not have much labeled data. So in terms of regarding the system that learns linguistic expressions, we've conducted initial experiments. So this is a paper that's still under review. We showed that our system, called RuleNN, outperforms rule learning baselines, such as MLN, Markov Logic Network Learning, and neural logic programming. Also, we showed that RuleNN outperforms black box classifiers from multiple instance learning, MINET. And RuleNN is also competitive with black box sentence classifiers such as BiLSTM, which it outperforms in the case of several of these labels. So this experiment is done on IBM procurement contracts. And, but more importantly, we gain interpretability over the black box models while still being competitive. So I mentioned the visual interface. This is what happens after the automatic learning of the rules. So we have a system called Heidel. This was showed in ACL as a demo this summer. The expert can look at the various types of rules and you can select rules or rank the rules according to their performance, precision, or F1 score. Moreover, you can look at the examples that are specific to each rule. You can see examples that are positive for the particular rule, also examples that are false positives. Furthermore, there is a playground mode where the NLP engineer can add or drop various predicates and see what the impact of that is. So for example, in this case, we can if we drop one of the predicates, the system says that the precision will stay the same, but of course the recall will increase. So, and it will quantify how much the recall will increase, and also what will give examples of relevant sentences that are now additionally classified by this rule. So this is Heidel. Now for entity resolution, I just want to mention that this is a long-standing research problem. It has been around for decades, but it's still very challenging and still very active. There are actually multiple manifestations of entity resolution. The more basic one, if you want, is the one that looks at string representations of entities. So here we need to be able to learn how to understand the name of an entity and how to normalize it. So this is an example of a company that has many different variations. Then the bread and butter of entity resolution is the most structured record linkage, where we have additional context associated to the various entities, and we can form rules to match those entities. And then, of course, this all leads into the knowledge curation and the creation of a knowledge graph based on structured entities and relationships from the raw data. And in one of the systems that we built, we actually use financial filings filed with the SEC and FDIC to construct a financial knowledge base that exposes an entity-centric view of the data. Just a few details on the entity resolution technology. So we have a system that is based on active learning that acquires labeled data on demand. This is system ER. It has two main phases. So it actually can start with no training data, so that's an advantage. And it requires some feature engineering, but the system comes pre-built with a library of various either generic matching functions or domain-specific matching functions for various domains. And then we learn explainable models in the form of rules. And then these rules can be executed at scale. We can run them on top of Spark or on top of Hadoop or other types of machines. Just to give some highlights of entity resolution, how the active learning algorithm performs. This is a scenario that I mentioned earlier where we match an internal employee database, in this case, with Twitter profiles. This is a sparse context because usually, while an enterprise database may have a lot of information for each record, something like Twitter will not have much information. But despite that, you can still produce a lot of matches. So here we compare system ER with the supervised general learners, such as SVM and MLN learning. But these do very badly. They have very low recall for entity resolution. So since these are more generic type of rule learning or machine learning algorithms. Now, if we compare with the learning systems that are specific to entity resolution, and in particular compare with active learning, so Arasu et al. Is a prior paper, and we showed that system ER outperforms it. So we can actually achieve, with 430 labels in this case, we can learn a set of rules that produce almost 10 times more links, while achieving a precision of at least 90%. And in general, active learning system that we build, they have high precision guarantees. So this is a system that we use in IBM to build industrial strength models for entity resolution and for knowledge graph construction. And we use it in particular in the healthcare and in the finance domains. And let me stop here.
Always try to bring the human in the loop, right?
Yes.
So bring human in the loop can bring some benefit. For example, people will feel more confident. However, sometimes you will sacrifice for lower accuracy. Do you see this trade-off, or you see some opportunity to have both benefit at the same time?
Sure, you can have a trade-off between precision and recall. In many applications, actually, in the industrial application, you want to be biased towards precision, high precision, especially for knowledge graph construction or entity resolution. You don't want to match, you don't have too many false positives. So we tend to be biased towards precision. But there is always a trade-off. I mean,